time. So it is my pleasure to introduce Michael Sobrepera. Excuse me. Before coming to Penn, Michael received his Bachelor's of Science in Biomedical Engineering from Georgia Tech. He's been my PhD student for the past 4 years. During that time, he has been incredible to watch and he's accomplished a lot. He took an idea that was pretty much a rough prototype of a robotic system that we were working on and definitely iterated on it heavily to a point where we now can operate it in the hospital environment. It is incredible that Michael kind of really learned the entirety of the robotic system and was one of those people who really took to the mechanical design, fabrication, the electronics, and developing the software control and everything to become, proud to say, a full stack roboticist. He's demonstrated a passion for mentorship, and he's mentored over a dozen students in my lab, as well as being able to participate in a variety of different mentorship opportunities for teachers in the community. He recently won a competitive NIH F31 pre-doctoral fellowship, and this fellowship requires him to put together a mentoring team as well as supporting the work that he's doing in terms of collecting data with his system. He's also actually been really involved beyond research, and he won the Rosberg Catalyzer and the Penn Wharton Entrepreneurship Startup Challenge. So he's been doing a lot, juggling a lot, and definitely showing that he is going to be a scientist to be reckoned with. So without further ado, I want to introduce Michael and give him the podium. He'll be talking about the design of Lil'Flo, a socially assistive robot for upper extremity motor assessment and rehabilitation via telepresence. Go ahead, Michael.
Excellent. Thank you so much. And thank you everybody for coming. I think this is going to be a really interesting talk, so I'm excited to share it with you all. I want to start off by giving an overview of the entire system, really letting the robot itself give an overview with this video that one of my students, Vera, edited together for us.
Hi there. I am Lil'Flo, a remotely controlled robot for telerehabilitation, and this is my operator. I was designed to help with upper extremity motor assessment and rehabilitation over telepresence, and can play games with patients. The hope is that by playing with me, patients will be more compliant and engaged. The user interface to control me is very simple. My operator can type in words for me to speak, change my faces, put my arms in different poses, drive me around, and have me play games like Simon Says. My operator can see the patient through my 3 cameras. I have many different faces, and my arms can be put in any pose. My operator can remotely drive me in different directions. I can play motor assessment games like Simon Says with the patient. Simon Says clap your hands. Simon Says put your right hand straight out front. That was fun, let's play again next time.
Okay, cool. So that kind of gives an overview of what we're going to be talking about today is this system, the design of the system, why we've built this system, etc. And so the why is the beginning, and it starts with the people who are interested in helping with this sort of system. And that's people who have generally upper extremity motor disability. That's normally when we're looking at it, we're looking at people who've had some sort of neural trauma. And so the video you see playing right now is of patients who have cerebral palsy. It's the most common motor disorder in young children. It affects over 500,000 children in the US. So that's 2 to 3 per every 1,000 live births, you're gonna see cerebral palsy. And it can range from people who have very mild disability, can play soccer and things like that, all the way to people who are wheelchair bound and can't move their mouth enough to eat. So there's a variety, and there's no cure for this. The thing is that rehab can have a really profound impact on long-term outcomes, especially when people are young. You can see this little girl right here has spasticity in her left hand. So that's where her hand is clenching involuntarily. And again, there's no cure for that, but if you can stretch her out as she's young, if she can do various strengthening activities, then she can end up in a better place. Now, in this other video, we have some people who have had stroke, and stroke is the result of, again, a neural injury where part of the brain is denied access to oxygen. That can lead to motor and cognitive deficits. Again, there's no cure, but rehab can have a big impact. And so rehab is one of these things where you have people who have the potential to live a full life, and without the rehab, they won't. And so it's really important that they get that rehab. The thing is that there are a number of challenges to rehab today. These come from cost. Rehab is really expensive. The people who do the rehab are highly trained, and therefore they have a significant cost. It comes from the geographic location of where the people live who need rehab and where the rehab can be provided. So a lot of people who have CP and stroke, they live out in rural areas or in low resource settings. And so they can't get into the cities like Philadelphia where you have a significant availability of medical care. We're also seeing large shifting demographics. So our population curves are inverting into this inverted pyramid where you have a lot of old people and not as many young people. And that means that the few young people you have aren't sufficient to take care of the elderly who are more and more surviving things like stroke, as well as the young people who are more and more surviving things like cerebral palsy at birth. And so that really leads to these supply side challenges where you just don't have enough rehabilitation professionals to take care of the load of demand. There's also a problem when you look into how rehab is done. You need to be able to track the progression of somebody over their rehab, so you know how to tweak it. Anybody who's done any sort of exercising is well aware of this. But doing that tracking is really hard, and there's a lot of subjectivity in it. And so we'll touch briefly on that at the end. But all this leads to there being fewer patient interactions, and there not being a lack of clarity with respect to what the patient's state is and how to continue to deliver their rehab. And we want to improve that so we can improve long-term outcomes. So there are a few goals that come out of this. And the first one is to develop and evaluate a robotic system, which you've now seen. So we have developed it, which uses a social robot to enhance telehealth interactions. Well, why would we want to do this? The premise is that if you have these distant interactions that can't happen right now, naturally, and now with COVID even more naturally, everybody says, well, we can use Skype, we can use FaceTime, we can use some sort of telepresence-based technology. The thing is that for something like rehab, we don't think that that's necessarily good enough. We think that you need a more present type of interaction that's easier to understand, especially when you consider that a lot of these people also have some sort of cognitive deficit. And so understanding over a screen can be limited. And I mean, this comes up frequently. I discuss this robot with a lot of kids. They come in for these outreach sessions, and I'll always ask them the same question, which is, if your mom was standing right next to you and told you to take out the trash, or if your mom called you on FaceTime and told you to take out the trash, which one are you going to listen to? And all the kids know that they're going to listen to their mom standing right next to them, but maybe not digitally, right? And so it's the same thing here. How do we make these interactions more real? And how do we make it to where when I tell you right now to lift your right arm out to the side, and that was all you just saw, we need to improve that, right? So I could stand back, I could lift my arm out to the side, now you can see it, but now you can't see my face, and there's a lot lost there. Okay. We also want to develop a computer vision-based objective diagnostic tool for upper extremity function to address some of those clarity issues. So if you have people working over telepresence, we think that you need more than just the video coming back to the clinician, and so we'll get into that a little bit. And then more recently, we've had some project goals develop around COVID-19. So the robot has been used a few times in the hospital. There have been some clinicians who've tested it pretty heavily. And so we'll get into a little bit of what we've been doing with that and some surveys that we're doing in the wire community to understand how robots fit in this new post-COVID telepresence imbued world. And so I want to keep diving into why some of this stuff would be a good idea. And so this is kind of our theory of how these interactions develop. Normally, when you're in person, you have instruction, emotion flowing back and forth. The clinician is able to motivate the patient to do rehab, which is oftentimes not comfortable and not that fun. And the clinician being present with the patient allows them to perceive the way in which the patient's moving so they can deliver some sort of long-term assessments. But when you just have video, you're going to have instruction passing back and forth. I can tell you what to do over video, and I'll be getting some noisy state data back. But it's not as rich. So we put this humanoid robot onto the Telepresence platform that you've already seen. And our goal is to fill in all that richness of the interaction. And so our first hypothesis is really that using this humanoid social robot will do that, and that will improve understanding, enjoyment, motivation, and compliance. And then that we can use video from this system to deliver some of these assessments that the clinician needs to be getting back. And this isn't something that's coming out of left field. There's literature that supports that this is a good idea. So this study with Man in 2015, they used a very simple robot that's really just a screen on a robotic avatar, as well as a tablet to administer some surveys and workout instructions to a series of participants. And they found that with the robot, people were more interested in doing the activities, and they were more honest with the activities they were reporting. And so again, the presence of that robot, even as simple as it is, seems to have a positive impact. Bainbridge in 2011 did a study that I really like, because they showed how robots can be used to drive uncomfortable tasks by being present. So the setup was, you have this robot that you see on the top left up here, and the robot could either be physically present in the room, or it could be on a video feed, but same robot regardless. And they asked people to do a number of tasks. So the first one was to greet the robot, and you can see there's no significant difference between the different conditions, whether it's physically present, video but augmented, or live video. Again, doing a simple task, like asking people to move papers from one desk to another, not significantly different. But what if you ask people to do a complex task, like throwing books in a trash can? You know, we're talking about like a stack of $1,000 of textbooks. Well, when the robot was present in the room, people did that over 60% of the time. But when the robot wasn't present in the room, it was under 30% of the time. That's a significant difference. And so what you see there is the robot's able to motivate people to do these things that are uncomfortable. And the same with reaching around the system, which is a socially uncomfortable activity to do. People have looked at various different ways that these projections could be done to see if the projection is important. So different sizes and scales, just the face, the whole body. The results are consistently the same, that having the robot present leads to better outcomes as far as compliance and interest and enjoyment. Frieden, as part of the RACCP Fund project, has done a lot of work that I find really interesting, because they've developed a system that's specifically designed for kids with cerebral palsy, and tested out a number of these questions. So here you can see they have a Now robot that's physically present with the child, or the same thing, it's on a video. And they had three conditions. Either you're seeing the video and you've previously interacted with the robot, you're seeing the video and you've never interacted with the robot, or you're seeing the robot. And they had a number of tasks, motor tasks, not dissimilar from what we're doing, that they tried out, and they showed again that the real robot was better. Interestingly as well, the virtual robot performs better if you've seen the robot before versus if you've never seen the robot before. If you've never seen the robot before and you see a robot on a screen, these children just didn't actually do anything at all. But I do want to draw the distinction between what they did and what we're trying to do. So whereas here, the robot it's a two-agent interaction. You have the robot and you have the patient. We're trying to drive these three-agent interactions where you have the robot, the patient, and the clinician. So in those videos you saw earlier, you saw the clinician on the screen up top, or in that case, me on the screen up top, whoever the operator may be. And we think that by doing this, you can make the interactions even more rich, but also allow the clinicians to interact with people who are far away. Whereas a system like this might be harder to bring that clinician interaction into the picture. Another project that I really like is the Now Therapist project. So they also use a Now robot, and they've been testing it with a variety of subjects, and it's actually now moving towards commercialization. And they've looked at how people react to this robot. And one of the things that's really interesting with this one is they use a computer vision system to measure how the patient is moving, and if they're complying with the activity, if they're doing a good job of doing these, Simon says, pose mimicking type of activities, the same type of activities we want to do. And then the robot is able to correct them. We take a slightly different tact in that we ask the clinician who's remote right now to do a lot of that work. But I think this level of autonomy is really, really cool, and it's the way that we'll end up moving. I think the entire field will end up moving. They've also looked at how people describe the robot. And so you see a number of adjectives down here that are largely positive: happy, clever, loving, beautiful, friendly, strong, polite. And so these kids are responding well to these robots. In order to do all this, they have a large software stack under the hood with some relatively rigorous math, trying to understand the state of the robot and the patient and the entire space that they're in to enable them to do these sorts of interactions. All right, so I want to move into the system that we've been working on. And I'm going to back up to that earliest prototype that Dr. Johnson mentioned earlier. And that was this right here. This is a Telepresence robot. So it's a commercially off-the-shelf available robot. And then a Now torso. And so the Now is mounted on top of the Telepresence system. It can drive around, it can interact in all the ways that you can program a Now to do. And this robot was tested in a number of situations with some providers to try to understand what sort of designs those providers might need. So those were rehab professionals in and outpatient hospitals, in and outpatient rehab hospitals, as well as a senior daycare where patients come in for the day, but then they live at home primarily. And so we asked them to rate the robot on a number of scales, whether it's intelligent, helpful, useful, social, or had good communication. And you can see the ratings here. It's generally positive. We also asked them whether they would recommend it, whether they thought it was interesting, whether they would want to exercise with it again. And so the interaction they did was they were shown what the robot was capable of, and then they did an activity with the robot. And so they would want to exercise, do that exercise again, whether they could see it as a companion in their overall impressions. And again, this is generally, we see as positive results. But the really interesting thing that came out of that and drove a lot of the future development of the robot, we're asking them for what they needed in the design. And so there are things that you'd probably expect, but it's always good to make sure that you're right when you expect these things. So things like needing portability and ease of setup. This first system was not portable. It was incredibly heavy. Lifting it was effort. It's not easy to set up. It's two totally separate systems that don't integrate. And so we needed to change how that was and really get to a single push button setup as opposed to pressing 3 buttons and turning on 2 computers and all that sort of stuff. That's not realistic. The cost is really important as well. And so this first system was incredibly expensive. The Now is an awesome platform, but it's over-engineered in every way. And as a result, it's overpriced for applications like this. The Telepresence system also was very, very expensive given the kind of compute power it had on board. It's a good system. It lasts a long time, but its screen is small. Its cameras aren't very good. And there's no way to really get into it to modify it. Maintainability is important, and I think that the prior system was pretty good for maintainability, right? You could wipe it down and things like that. The Now robot, or at least the Telepresence system was good for maintainability. The Now robot had problems both with maintainability and durability. Anybody who's used Now knows that the motors like to overheat, knows that when something breaks inside, it's a serious effort to fix it. And so we wanted something that would be able to close the gap there on maintainability and durability so that it could be maintained in the field. If it was ever deployed. The other things, appearance, I think this thing nails appearance. It's attractive, and we've tried to nail appearance again with our newer systems. Noise level is always a challenge for these sorts of systems because noise can disrupt interactions, but noise also costs money, or low noise costs money. And so that's been continued to be a challenge for us. And then people mentioned that they would like it to be used for supervision and observation. And you see it's a little bit different depending on where the people are. And that's kind of what we would expect. We also asked them for some open-ended needs. Again, what you take away from this is just that the needs of a senior daycare and an inpatient-outpatient hospital are different. They treat different types of patients with different types of objectives. And as a result, their needs diverge. And so you need to be cognizant of that when you're designing as to whether you're trying to design for both of them or one or the other, and how that interplay will work. So with all that in mind, we began to design a new custom system to be fully integrated. So beginning of my PhD, I started off with something really simple, throwing together prototypes with a create base for my robot, and then this BioLide robot from XYZ Robotics. It's essentially a series of motors with a microcontroller similar to what you would get from a Dynamixel, from anybody who's familiar, and then putting a camera on top. We quickly realized that we needed a little bit of help from some designers. And so we brought in a well-known robotics designer, Carla Diana, to help us begin to create a form that would convey what we wanted to convey. And so here are some early sketches, and you can see there's a variety of themes. There's a sort of spaceman type theme. There's an animal type theme. There's more of a doll type theme. And so the animal theme kind of evolves down here. The spaceman evolves into here. And the spaceman is kind of what we've moved forward with. And we did that intentionally. We wanted to make sure that the robot wasn't biasing the interactions based on how it looked towards one group or another. So because it's a kind of spaceman type look, it doesn't look like any particular person, but it still has a humanoid form that's easy to understand. And because of that, we hope that a large group of people will be able to interact with it, have some sort of shared empathy with it, and drive positive interactions. So the head on the robot is what we consider to be the source of the social interaction. And the social interaction we think is important because that's how you're going to motivate people to do these activities and to be able to enjoy them and want to do them again. And so Carla helped us develop a bunch of themes for heads, and then we started prototyping them. And so here are some, I think this is actually the first 3D printed prototype we did of the head. And you can see that we were looking really just for form and for scale, not really for mechanical soundness. And you can tell that the form and scale aren't right. The head is clearly way too wide for this body. The eye and face positioning is not right. We immediately realized, like within 30 seconds, that being able to see these screens was awful. And so we put some paper or tape or something over it to try to diffuse that a little bit. But these sorts of iterations are what you go through to begin to develop something. And we continued iterating, and we ended up with a form that looked like this. And you can see that the mechanics still aren't quite right. We're not sure how we're mounting any of this, but at least we were happy with the form. And then this is the final iteration of the head and face. And so you can see that one of the things we've done is really hide the seams of the head. So right here, there's a seam that runs along the forehead and then it goes back behind the ear and down. There are smooth curves. There are ears. We looked at versions with and without ears and did straw polls in the hospital to see how people were reacting to that, how other researchers were reacting to it. And we found that the ears conveyed a greater sense of comfort and that they made people believe that the robot could hear them, which is positive for social interactions. But then the question is, how do you put a screen onto this thing? And we didn't want a screen that was bolted on and glued on, was gonna have messy seams. And so what we actually do is we mold it in. And so we take the 3D printed part, we have a positive that we've made of it in some silicon, and then we mold in a clear urethane that we add a dye to. And so you end up with something like this, where you can't really see the LEDs behind unless they're lit up. And you can express a ton of different faces. And so these are faces that another designer helped us come up with. And what we were trying to do is to express a wide range of emotions with these, because we want the robot to be able to convey its emotion to the subject, or the patient. And we did a small study to test what these emotions were actually saying, because we had an idea, we had named them, but we wanted to see what other people would think. And so we just took the head of the robot, mounted it on top of a box covered by some black sheeting, recorded video, and we asked people how they felt about it. And so there were two phases to the study. The first one, they just sat there observing the robot and answering some questions about the robot. And there were two modes for that. So the robot could either be dynamically changing its face, looking around so the eyes can look different directions and things, or it would just be static on its default neutral face. And halfway through that first section, those modes would switch. So if people who saw it statically initially would then see it dynamically, people who saw it dynamically initially would see it statically. And then the questions that we were asking them were mirrored across those two, different wording, but the same general theory, and then we randomly ordered that, of course. And then in the second part of the study, we asked people to name the word. So we showed the subjects, every face that the robot had in a random order and asked them to tell us the first word that came to their mind for each of those. So the first part of that study didn't tell us a whole lot. That's not terribly surprising. We only had 10 subjects. People were generally friendly and comfortable, or generally found the robot to be friendly and were comfortable around it. They didn't find it to be as trustworthy, which is somewhat reasonable since it had its body hidden. So we got a lot of open-ended responses that how can you trust something that you don't know what it's doing. People did find it machine-like, and that's not a negative to me because we don't want it to be a person that falls into the uncanny valley. We want it to be clearly a robot that you can then develop a connection with. And we looked at different ways of interpreting this data, and it didn't really matter how you sliced it, you didn't get much significance out of it, and that's okay. What was really interesting, though, was getting the responses back from the words that people thought were associated with each face. So we coded these words down to a condensed set, and then here you see all the words that had at least 3 responses. What you'll notice is that in some of the columns, you have very strong responses. So here you have 8 responses saying that this face is sad. Here you have 5 saying this is happy and 2 saying it's neutral. So in fact, we changed from One of the other faces, I believe it was this one that was our original happy neutral face, to using this one as a learning from this, because this face didn't really give us so much happy. It gave us some creepy, and we didn't really want creepy. And so these are the kinds of learnings we were able to take from this. Like even these small little studies, you can say, well, obviously our interpretation was wrong, right? N of 10 is much better than N of 2 on the designer side. And so these are great learnings. From that, we were able to narrow down the number of faces we were interested in and give them a new set of labels based on these responses. And so these are the labels you see. And again, like this face wasn't one that we thought was default neutral happy. We really didn't like that face, but other people did, and so that's what we're going with. You can see we've got a range of sads. It seems to be a little bit easier to express sadness at the moment than happiness, but I think that we've kind of covered the space of the emotions we would want to express with the robot, and that's really cool. So now that we've got the head and the face kind of figured out, it's time to move on to the body. And the body, remember, is not here as much to convey emotion as it is to convey the meaning of what the activities are and to drive these interactions forward in a physically present way. And so that means that the arms need to be able to move around, and they need to be able to move through somewhat of a human range of motion. That's not exactly trivial to do on a small robotic platform like this. We use these pre-built motors because it significantly lowers the cost to design, it makes it easier to maintain, and it makes it easier to program. And so the question was, how do you fit these sort of boxy motors into these arms? And so finding an arrangement that worked well was a little bit challenging, but then also finding the forms that were pleasing to look at was a challenge. And so Danielle Chen was another designer who came and worked as a mentee of mine over a summer. And so she really iterated a lot on these forms and came up with the idea of having these sorts of mittens, of getting some of the tapers into the body, into the wrists and that sort of thing. And then I was able to take the design work that she did and turn this into an actual mechanical design that you see here to shrink everything, to make it all strong, make it all fit together. There are some important things to note here. So one is that you can see on this arm that the shell of the arm is actually the exoskeleton. So there is no internal structural support for the system because there's just not enough space. The other benefit of doing it this way is that you have minimized the amount of screws. So if you need to maintain it, if one of these motors manages to burn up for whatever reason, then now you're able to pop open the arm. There's not a bunch of structure in there. It's just all screwing straight onto the motors with one screw down here at the hands. Another really important design requirement for us was that you not be driving a lot of pinch points here. So you don't want to have a situation where a kid reaches in, touches the elbow, and ends up with a bloody finger. And so we put a lot of effort into how do you think about designing these sorts of concentric motions into the spaces and having these sweeps. You can actually really see it right here, that if you imagine putting a finger here as this is rotating around, then the finger would not be allowed to enter, all right? And so you would avoid pinching. And so that's really important. And so this is what those arms look like actually fabricated. We've just 3D printed everything. But in fact, most of these parts could be, unlike the head, could be turned into injection molded parts if somebody wanted to do that. Of course, you would totally redesign this before you were able to put it into production, but thinking about how you would make stuff maintainable at least is important. Another thing I want to note, another challenge, is getting wires around these sorts of things. So we use external wire routes that are hidden as best they can be behind the elbow and the shoulders and things like that. But that's kind of the best you can do affordably and while keeping things as small where slip rings wouldn't really work. One of the things you should notice here, though, is that these prints are messy. And a lot of times, I think when people develop these robots, this is close to the final form that they take. They leave it in its printed form, they maybe sand it a little bit. But it was important to me that we build a system that looked, even if it's not being built with production grade technique, that looked like it was production grade, so that we're testing against the ideas of making a system as production grade. And so we spent a ton of time post-processing all this and building what is, I think, actually a pretty beautiful robot. There are some explicit design choices being made here with the colors of the system. So the torso is black, and then you have these alternating joints that are black and arms that are white. And that's to drive contrast in the system. So we wanted people who might have visual impairments, who might have cognitive impairments, et cetera, to be able to see this robot and understand where things are going. And so having a constant color scheme wouldn't do that as well. And this high contrast black and white, you're going to really maximize the amount to which people can see that. I mentioned that being able to move through human range of motion is important. And so here are the range of motion measurements. They don't mean anything on this table, but this means more. And so you can actually see some of the motions the robot can do, right? You've already seen it wave, you've seen it clap. You can put its arms out to the side. Some kids at an outreach event asked me if I could program it to dab, and indeed you can program it to dab, and that made them very excited. That actually gets responses in the hospital as well. People love that. But down here you can see a limitation. So this is as far as the arm can curl itself in. And that's not realistic to humans, right? So 90 degrees, we can go almost to 0. And that does limit some of the activities you can do, but it's a reality of designing these sorts of systems. There will be limitations. The other big limit is that we ended up going with these mitten type hands. And so that simplifies the design. It allows you to have low weight at the end of the hand, so the motors can be cheap. But it does mean that the large space of fine motor tasks are really impossible to truly do with this robot. And fine motor tasks are really important for people in our population. So you can still do things like telling the robot, like the robot could say, you know, to button your shirt, and it could kind of tap on its chest as it pretends to button its shirt. But there is a limitation there. So one of the initial project goal 1 was to develop the system, and I think I've shown you a lot of that development, but it was also to test whether it actually works. And so when we went towards developing the base, we wanted to make sure that the base and the humanoid interacted in a way that we could actually do a rigorous study of whether the humanoid is affecting interactions. And so the way you do that is that you make the robot able to come off. And so here you can see the base with and without the humanoid on it. And so we can develop studies that are around that capability. The base itself is made up of a kabuki robot, which is a standard off-the-shelf mobile platform that's used by roboticists to build these sorts of systems. It's got a battery pack very low on it. It's got a Nook computer. It's got a screen, a series of 3 cameras, so 2 RealSense cameras and 1 fisheye camera. And it's also got speakers. And in fact, now, after having tested it in the hospital recently for COVID, we've moved away from this speaker. We now have actually 2 much bigger speakers that are hidden behind the robot. Because it turns out that people can't hear as well in hospitals. We should have thought of that, but that's why you test. So here's how that's all wired up. The inside back of the robot is a little bit of a mess, but it gets the job done. A significant limitation here that anybody who's worked with the kabuki will note is that there's a separate power system for the kabuki and the rest of the robot. And this power system isn't integrated. So right now, if you want to know the power level for the compute stack, for the humanoid, and for the cameras, you have to look at these little dots right here. That's very much non-ideal, but it's good enough for us to do the kind of testing that we need to do. And so we move forward with that. So I mentioned there are these cameras on here, and earlier on I mentioned wanting to do these perception pipelines, and so these go together. The idea of the cameras is to be able to watch people who are doing interactions with the robot, measure how they're doing those interactions, and tell the clinician what they're doing. The second goal of the cameras is to allow the remote clinician to be able to actively understand what's going on in the situation and be able to manage the robot in real time. So we looked at a bunch of different configurations for cameras. We tested it out with some clinicians over at CHOP. And there are different benefits to different setups, right? So this setup and this one are nice because they keep the cameras low to the ground, the total height of the system's reduced. That's positive. This one and this one are nice because the RealSense cameras are perfectly aligned. So you can see they go off from almost the same origin. And that means that stitching them together is really, really easy. And that's convenient for doing processing. Downside is no matter what, you're losing some sort of field of view up here on top. So we ended up going with this mast rising up above with 1 camera looking down and 1 camera looking forward. And with this, we're able to maximize what we're able to see. We do lose some of, I didn't mention these, this is a young child and then an older child, I want to say like 14 or 16, just based on norms. And so you do lose some of their arms, but it's better than the other systems. And then you can see the fisheye camera covers the entire space. And the fisheye camera was, again, something we added from testing with clinicians where they used the system, they said immediately, like, nah, this isn't going to work because kids are all over the place. Our kids are all over the place. The patients we work with are all over the place. You need to be able to see the whole room. And we have parents who might be in the room we want to be able to see. And so we added a fisheye camera. Again, the power of these like quick, rapid tests. These are depth cameras. I haven't mentioned that. And so these little red zones are areas you can't see. So that's another challenge you have to work with. In like this sort of setup, you can see that close by, you're gonna be missing some stuff. Okay, and so this is what that ends up looking like. You can see that you can see my upper body when we're doing a remote activity, things like a Simon Says type activity. And then you can also see my hands touching the robot when we're doing a target touch activity. And so this is useful because one of the big indicators of function is doing point-to-point motions. They're relatively easy to analyze. There's a lot of literature on how point-to-point motions should look like. So when someone moves your hand from one place to another, and this really simulates that. The Simon Says is really interesting because you get these more macroscopic motions. They're not as well understood, but you also get range of motion, which is very well understood, easy to extract, and has direct clinical meaning to every clinician. If you tell them that here's the range of motion on this shoulder, they know exactly what that means, and that's really powerful. I'll note that we tried an earlier version of these cameras where like one of the cameras from the prior slide, where one of the cameras was really low. That was another sort of like awkward moment where we realized that, you know, having cameras low on a robot is not good for social interactions. People realize there's a camera down there. Nobody wants to be seeing it or be seen by it. And so thinking about how you place these cameras is really important. And maintaining privacy even when people can see the robot. And so then we tied this all into this web-based interface. The interface is designed to be easy to use, but also give a clinician all the control they would need. And so you can see the views from the different cameras, as well as the view of yourself. You can also see a rendering of the robot, so you know where its arms are, because seeing it, you can't always see the arms here. You get some system stats because it turns out, go figure, that in hospitals, Wi-Fi isn't perfect. And you'd like to be able to know when your Wi-Fi is dropping off before you drive into a dead zone. You drive the robot by clicking in this circle, and the robot moves in the way you would expect for a joystick. Almost every clinician, when they've tried this, at least any clinician over the age of like 45 when they've tried this, has found this to be a little bit difficult. But people who found it to be difficult after 5 minutes say it's great, and they've actually really enjoyed using the interface. And I've asked them if they want something else, and what we've heard back is that they actually like that. So that was good. We have the various faces you can display. So you can click on the face and you'll see it, and you can also change the brightness. It turns out, again, from testing, that people were getting creeped out by the brightness being too bright. And so we made it to where you can lower the brightness actively. All the motions that the robot uses are composed of a series of poses that can then make a sequence. And so poses are the static points where the robot can be. You can orient those poses for the left and right arm in sequence, and then dictate the amount of time from the prior pose. And we did time from the prior pose as opposed to something more complex like velocities and accelerations, because we wanted this to be, again, simple for a clinician to use. And so the robot just uses very basic trapezoidal velocity profiles. There's just a fixed acceleration that we always use. And then the height of that trapezoid is dictated by the time. You can save these sequences and poses out, and so you can actually move the robot physically in person and save a pose, or you can drag some sliders around here to make a pose and then save that. The sequences can load in, you can edit them and everything, and then you can use these poses, sequences, as well as text to build up what we call game buckets. And so a game bucket is a series of poses and sequences that can then be used in a game in order to drive an interaction. And you would imagine that for every subject, that game bucket might look different. So if a subject has significant involvement on the right arm and little involvement in the left arm, you really might change how like their left and right arms are being asked to act. If somebody's got, you know, they're only able to get motion out of their shoulders and their elbows are locked out, and you know that and you don't want to demotivate them, then you might be doing primarily elbow-based activities. And so you can customize that for every subject, and then you can run the games. And so right now I mentioned we have this Simon Says game, I have this target touch game. They work exactly the way you would think that those things would work. Either the robot is saying Simon Says or not saying Simon Says and asking people to do things, or it's putting its hands in different positions and asking them to touch them. What's important here is that, again, we've endeavored to give the clinician as much control as possible. So they have the ability to go next, to repeat the last task, to say congratulations in a number of ways, randomly selected from a bucket of congratulations, to try it again, to quit the game, etc. And so by doing that, you really bring the clinician into the interaction, because you don't just have to be concerned with bringing the patient in, but you have to make sure the clinician feels welcome by the system, that they feel like they're in control and that they are really maintaining their connection with the patient. And so under the hood, I don't want to get too much into the software other than to say that it's a ton of software. The programming effort to integrate a system of this complexity without even having autonomy built in is absolutely huge. And so we use ROS to do that. But there are a bunch of different modules we've had to build into that, modifications we had to make to other people's modules. We use AWS for text-to-speech. We had to make some modifications there. And then we use ROS WebRTC to get all the information that we want on and off of the robot. And then ROS Bridge, to get all the the video information. So WebRTC is web real-time communications. So that's video, audio, and some data. And then we use ROS-Bridge to actually move the various sort of messaging data that you might have. With moving towards COVID, it became apparent that we would want to do things beyond just testing in our lab, or me bringing the robot somewhere and testing in like a short distance. And so whereas all this was originally being done on a single Wi-Fi network, as people generally do with robots, earlier this year became apparent that I should scale that out. And so I did. So we have a pair of servers that run over in New Jersey in a server farm. And this manages all these communications going back and forth. Again, this is complicated. It's been really, really interesting to learn this entire web stack and learn how do you deploy systems into the cloud that can do all these sorts of communications. How do you tie together multiple databases with multiple microservice servers and all that sort of stuff? And then how do you make video go over the internet? Because a real challenge in any healthcare situation is that you have to be very careful with what you're doing on the network, respecting the firewalls and that sort of thing. And so we use video that's encrypted end to end, but even still the standard methods of transmitting it wouldn't work in a hospital. And so we had to have extra servers that manage sending all that information back and forth and making sure that it's all very secure, it's all using industry standard certificates and that sort of thing. So that's all been done. Continues to be an effort to find bugs, but it's a huge stack as well. And so I wanted to talk a little bit more about that COVID and kind of what happened. And when COVID was building, a couple of the clinicians in the hospital knew that we'd been testing out these telepresence systems, and they said, hey, listen, we might want to test this out because we have these rooms. We don't know if we're infected. We don't know if the patients are infected. Could we just be driving the robot into the rooms to minimize the contact, right? Right now we have 3 to 6 people go into the room. Could we just have one robot go in, just at least to ask questions? And we said, well, not right now, but we'll build that whole web stack. And now the robot's done that. It's gone into, I think, 3 patient rooms as of last week. And that's after dozens of hours of testing it with the clinicians and understanding what were the needs they had. And we actually built out 3 systems for them. So the one that you've been seeing here, as well as we took the flow system you saw at the beginning, we took off the now, and we just tried that one. And then we had a third robot that was an older commercial system. And we really compared the Vigo, which was that commercial telepresence system, to ours. And what we found was that it was just so much easier to control for the clinicians, that we had built this integrated system that worked in ways that they found intuitive and that we could customize to them as needs came up. And so there was it's clear that having a competency in how you build these things, specifically for the needs of the people who are using them, is important. But we want to do some future testing. So the kind of testing that we can do in a hospital in that sort of open-ended setting is limited. And so we have 3 tests that we're spinning up right now. The first is a feasibility study, and that's going to understand how clinicians and their patients interact with Lil'Flo in somewhat of an open-ended form. So we'll just ask the clinician to run the Simon Says game with their patients, and these patients can be from a wide variety of needs. They can have upper extremity disability or not. They can have cognitive disability or not. They can be, I think we put age 4 to 100. And the reason why we're being so open with that is because we want to just see how these interactions develop. We're curious to know how the clinicians would use the system. And then while we're doing this, we'll be trying to, when possible, collect video so we can hopefully build some of those assessment pipelines. The second study is really the study that we started off wanting initially, which is this interaction mode study. So understanding when the robot is there versus not there. And again, we'll be measuring that with surveys. We'll be looking at video. So is somebody enjoying it? Well, you can tell that by seeing if they're smiling, et cetera. And the third thing that we're actually up and running with right now is we're running this broad survey of any professionals in the rehab space. And so we're asking them about how COVID has been interfering with their practice. How have they been able to use telepresence? What has and has not worked for their telepresence or telemedicine? And then we asked them about this system. Where could they see it going? And in general, for robots, is the field afraid of robots? Are they excited about robots? And so we asked those sorts of questions. With that being said, if you know rehab professionals, that could be physiatrists, occupational therapists, physical therapists, et cetera, it'd be great. I have a survey link. It'd be great to be able to pass it on to them. I'd really appreciate that. So just let me know. Here's where we're planning on doing those studies. We can skip over that. I want to touch briefly on that assessment pipeline and really just the vision of what we have. So this is somebody doing a box and block test. It's a standard clinical assessment where they move boxes from one side of move blocks from one side of a box to another. And if you say someone's box and block score is X, many clinicians will have an idea in their mind as to what the functional level of that patient is. And so the question would be, initially, could we develop assessments that from video of this person not doing the box and block score, them doing a Simon Says game, could predict their box and block score? And if we could do that, then perhaps we would know that we could build these even more interesting assessments in the future. And other people have played around with these sorts of things a little bit. So here's an example where Curdio took Connect camera. So Connects, when they hit the rehab space, were huge. If you type in like Connect in upper extremity rehab, your pages will be full of hundreds of results. But this is one of the really robust ones where they were looking at reachable volume and different ways to define that volume and what that meant about functional level. And the reason why you might do some of this stuff is because there's a large theory behind, range of motion is obvious, but on movement, there's a large theory as well. So on the top here, you see somebody trying to draw a circle soon after they had a stroke. And their motion breaks down into these primitives. You can see on the velocity curve, these peaks, but then also on the actual spatial curve, it's broken down. Here's twice as long after the stroke. They're starting to build a circle more smoothly and more easily. And then here's a healthy person who can draw a normal circle. And so there are these theories on how the motion works. So if you can extract the kinematics, using, it's a little bit older, but using open pose or something similar, which extracts kinematics from video, then you can draw these sorts of curves of motion. And you might be able to start to say, oh, this is me being healthy, right? So I'm very smooth, but somebody who's not healthy might be less smooth. I also want to talk about ethics here because I think that we as roboticists in particular have a responsibility to discuss ethics. We're promoting systems and developing systems that could radically change the way the entire world works, but really how healthcare works. And so as we develop the system, we've talked to a lot of clinicians about this and we've heard their fears, right? So this past week when I had the robot in the hospital, I don't know, maybe 15 people that I saw were excited about the robot. They were laughing. They were taking selfies with it. These are all clinicians. One person came up to me and said that she's from Central Africa, from like a mountainous region, and that she would love to understand like how these systems are going to be developed for places like that, right? And so I mentioned cost earlier. We're not at that cost point. We're nowhere close to it. But that's like, long-term vision. That'd be incredible. And so to see people that excited about it is really positive. But we've also had clinicians come up to us and say, this thing's going to take our jobs. This thing's going to decrease our interactions with our patients. This thing's going to make medicine cold. I had one clinician last week say that was just creepy. And so engaging in these conversations is really important. And I want to really encourage those of you who are roboticists here to think about these things, right? Why have we decided to pursue telepresence instead of going wholesale automation? Well, because we want the clinicians to be involved in the care because they are really the cornerstone of the care. Why have we made considerations like making the robot black and white? It's because we're trying to be broadly applicable to as many people as possible and not pick one person. Why does the robot have a form that doesn't look like any particular person? Again, to be broad. And so I think we have a responsibility to develop these systems for the people who need them. I think failing to do that would be a waste of resources. But I also think we need to be careful about exactly what we're developing. And this also goes into the data collection, right? Like, how do you responsibly collect data? We're building these algorithms of how people move. How do you responsibly build algorithms that aren't biased to one person or the other? It's all really important. And it's been exciting. In GRASP lately, we've been having more and more talks about this, and I hope that continues. All right, I also want to mention some of these side projects, and this is really directed towards the younger PhD students in the crowd. My first couple of years, I don't think I did as much on the side outside of research. I did a lot of sailing, I guess, but more lately, I've been exploring what Penn has to offer, and it has a lot to offer beyond just in engineering that I highly recommend y'all check out. And so this is, now it's called Mario Orthotics, but a venture that Ariella, Rebecca, and I started. They're two other PhD students, for those of you who don't know, in mechanical engineering, both roboticists, building orthoses for kids with CP. And so I mentioned spasticity earlier. Kids wear these braces for spasticity to stretch them out, and doing that stretching, again, early on in life is really important, but they're super uncomfortable. So it turns out they actually don't wear them that often. And beyond that, nobody's actually sure how much they wear them. The parents just say they're not wearing them. We don't really know how much. And so there's this whole, we developed this venture to try to improve on that space, to build orthoses that were dynamic, that could react to kids, etc. That's not what's important. What's important is that how cool it is that we were able to do this at Penn. So we went and joined the Penn Health Tech Rothberg Catalyzer. And so Penn Health Tech is this body that sits between engineering and medicine and kind of tries to bring the two fields together. And so we ended up winning that. And then we also went over into the Wharton Startup Challenge and ended up winning their Innovation Award. And it was really cool to be welcomed into Wharton, right? That's somewhere that a lot of the engineers kind of stay away from, but the expertise over there and the excitement for doing stuff like this, it was really neat. And apparently we're one of the first engineering PhD groups to really break over there and to be as successful as we were. And so I'm hoping that more engineering PhD students will at least go play that game. I've also done a ton of outreach, and I think outreach is really important. I think it actually falls into the ethics discussion a little bit. We shouldn't be developing these systems in isolation. We should be developing them with the community knowing what we're doing, talking about it, and getting the education broadly, at least the interest, to be able to think about joining us in developing them as researchers or as engineers or as even business people, whatever it may be. And so doing things like the Research Experience for Teachers program, going to schools, doing outreach events here, I think those are really important. A lot of times it's the same group of people doing these outreach events, and I really want to speak to the crowd and encourage more of y'all to come join us in these, because they are really impactful and they're one of the most fun things you can do. They take a lot of time, but they're really awesome. I also have a note on pacing for the minute we have left for the younger students. What you've seen here all falls within the scope of my qualifying exam. So I'm starting my 5th year and I still haven't finished my qualifier. And I actually reread my qualifier proposal yesterday, and it's kind of laughable. I can't believe it got past whatever review it went through. But when you're starting to work on these things, right, you have these broad ideas, and then you're gonna go deep and you're gonna realize how much harder they are, and it'll keep getting harder and harder and harder, and that's okay. I don't think anybody told me until the end of like my 2nd semester that, you know, it was okay that they hadn't finished their qualifier either. So if you start asking older students, they're all gonna tell you they haven't finished their qualifier, and that's all right. All right, I want to close by throwing up, these are the papers that we've been discussing today. I'm now being funded by the NIH under this F31, so huge thanks to them. And then I've mentored a ton of people in the lab, and in many ways they've mentored me as well, and I've grown from them. And I hope that they've grown from me as well. Mentoring has been one of the really exciting things about the PhD. I think it's the thing that makes academia the most exciting to me, and so I hope that all of you can go mentor some students as well. And with that, I think we're good to open up for questions.
There weren't many questions in the chat, but if anyone has any questions, we are able to take that right now. There's one question that just popped up. Ariella?
The question is, have you heard reports of any differences in interaction of patients with social robots based on their cognitive abilities? How specific is the target for Lil'Flo? Yes, I have. So there was a study that was done looking at, I think it might have been within the RECCP fund protocol, but different than the one that I popped up earlier, where they had different types of children that were interacting with the robot. And one of the things that they were looking at was on that first interaction, what do you need to do to make that a positive interaction? They found that for certain populations, and I believe it was for the kids who have a cognitive deficit, that there needed to be some sort of like initial introduction. So if you just dropped the robot in front of them and told them to play with it, that could disturb them and scare them. And so, whereas the typical kids, some of them would be also disturbed, but more of them were able to just jump into the interaction. So thinking about how do you introduce a robot with a person there, telling them who it is. And I think that's actually another positive for our system, is that by its very design, the person is coming with it, right? So the robot is never in isolation. And so that's, yeah.
So I'll handle the question. So the other question is from Jessica. She's asking about whether there have been any studies on whether people become less responsive to robots over time. Is there some novelty effect that is important?
Yep, there have been a lot of studies on that. So as you start to get longitudinal data, then you definitely do see a novelty effect that wears off. But just because the novelty effect wears off doesn't mean that the interactions aren't still positive afterwards. So the Now Therapist project has run for, I think, up to like 14 or 15 interactions with large cohorts of subjects, or large for us, it's like 12 subjects. And they have shown that the interaction remains positive.
There's another question about the iteration, like before we had legs on the social robot and then we moved to just the arms. if you can comment on that and whether our goal is to have both arms and legs. Ultimately, yes, but comment on how we ended up just going to arms.
Yeah, so it was really just a question of time resources. So everybody that we're going to be testing with for right now, we expect to be seated for safety. The robot's not designed to hold a patient up, and unlike where you see in this slide from non-therapists, they're interacting with relatively high functioning patients. We expect to be interacting with a wide range of functional levels, and so being seated is important. That means that legs won't be very involved in the kind of interactions we're driving. Long term, we would like to get back to having legs, but for right now, we thought we could do what we wanted to do without them.
Okay, you have a question about survey, the design of surveys. Spencer asked if you rely a lot on surveys to assess the performance and efficacy of Lil'Flo. What are some important principles for designing a survey that gives you valuable and unbiased insight? And how do you phrase the questions, choose the rating scales, etc.?
Yeah, I think that I'll be honest, I think that's one of my weak points. I don't know that I have and it takes a significant amount of experience to know how to do that as best as possible. But the principles that I try to apply, the number one principle is to use surveys that other people have developed, so not to do it myself. And then that kind of allows me to escape that problem. So people like, I think it's RACCP Fund has this child interaction scale. We can use stuff like that. NASA has the task load index scale. And so that measures how hard tasks are. And we can't directly use it, but we can take very close inspiration for it, change the wording a little bit, and then use that. And I think that's really actually important as a field as well, because right now what happens is you read every paper and everybody's using a different scale, and then you have no clue how to normalize between studies. Like doing a meta-analysis in this space is almost impossible. So,
but one thing to mention, Michael, is that you have sought biostatistician help in designing the survey, and that we have also vetted the surveys with your target population as well.
Yep, exactly. That was even the next thing. And not just them, but also with clinicians who work with the subject. So I'm actually working on rewriting a survey right now because I passed it by some clinicians before we're about to begin studying. We began the study and they were like, well, this is great and all, like the questions you're asking, the things you're looking for are what you should be looking for. Problem is that a lot of our kids can't use sliders. Like they don't have the motor control to go to use a slider. And a quarter of your questions are sliders because mathematically I really like sliders. So I have to go away from a slider scale and do something where a kid who maybe can't even, use their hand to write on a piece of paper or touch a tablet can say, oh, number 3. So testing it is really important. Seeing if, but I do think that, yeah, there's a lot of relying on other people's expertise is the trick at this stage in the game to make them just too early on in my research career to do it on my own. And even Dr. Johnson, right? She's done hundreds more surveys than me, I would imagine. And so we go through the surveys. I don't do it in isolation.
Yeah. So you have a couple of questions about exposure. So what kind of reactions have you had from older patients who may not have had previous exposure to the robots? And I think there's a follow-up questions about comfortability, how comfortable are people with the height, size of the robot? I think they're related, those two are related to each other.
Yeah. And I think it brings up a good point about the size of the robot being small. So the actual stature of the humanoid itself is small. It's on me about yay big. That means it's non-threatening, and I think that people get that, and it's really cute intentionally, and people seem to get that as well. I have yet to have an older person react negatively to it. I have had actually more people in their 30s and 40s react negatively to it because I think they grew up with Terminator, and like any robot just kind of scares them. But even them, once they interact with it a little bit, it seems to be more positive.
Yeah. So Dio had a question about global context. He says that it's amazing that you're working to apply this technology to a variety of global contexts. What steps could be taken to drive down the cost in future iterations?
Yeah, it's a good question. And I mean, so when you look at where the cost comes from on the system, it's coming from motors and it's coming from compute power and then coming from cameras. Cameras continue to drop in price. And so whereas the camera that's in your phone today cost a few $100s 10 years ago, now it costs $5. I think that the stereo cameras that we use for vision will do the same thing. We're already starting to see them pop up on tablets and phones. AR is becoming a big thing. And so the cost of that will come down. And we might even discover we don't even need 3D, that we can do everything we need to do with 2D. And then the cost, that's like $300+ off the top right there. Motor cost is much harder because motors are just expensive to build. I'll say that there are some people here in Mark's lab who've done some really cool stuff with making lower cost motors that work well. And certainly designing from the ground up can decrease price significantly. So if you look at, there are a couple of systems that have come out in the market recently that are driving total hardware cost into like the $100 range, which is getting a lot more realistic. And they do that largely by engineering the system from the ground up and then building at scale. So that helps a lot as well.
So you have a question about the number of motors that you actually use for the upper limb. And the question was, how many are they in total? And what platforms are you using to control them all?
Yeah, let's pull up the one of the arms. So there's, let's just do one arm. And so there's one right here in the chest to drive your arm rotating like this up and down. And then there's one right here that controls your arm going like this. Then there's one right here that controls your elbow rotation. And then one right here that controls your ability to curl your arm up. And so that's 1, 2, 3, 4. So 8 total. I think that's right. I should know that off the top of my head, but I don't. And then for controlling them all, they're actually all controlled by a microcontroller that sits inside the chest. And that microcontroller connects via USB to the central computer. And so they're all controlled over serial. I guess I should specify that the microcontroller connecting to the motors, these motors, like I said, they're like Dynamixels for those who are familiar. So it's actually, it's not a current or a stepped signal that's going to the motor. The motor actually receives a serial signal as well and then has its own controller internally.
Okay, you have a question about the decision to have kind of a 3-agent system, the clinician, flow, and patient, instead of merging flow and the clinician as one entity. Or the other thing is, could flow behave as a peer to the patient, perhaps for children, who's also participating in the rehab activity to motivate the child? To talk about what the rationale was behind that.
Yeah. Yeah, so that word peer is actually a word we use a lot. I'm surprised I didn't use it in this talk. The reason is because we wanted somebody that would want to exercise with and play games with the robot. And we didn't think that some clinicians are filling that role, some aren't. And so we definitely designed it with this eye towards it being a peer. I think the other thing that we think about long term is, as clinician shortages get worse, how do you start to begin to meld or blur the lines between systems like this and like the RACCP or the Now Therapist? And the idea that some clinicians have talked with us about is building systems where a single clinician is interacting with multiple patients at a time and hopping between them. And so you can set up, you go in, you set up the patient, you talk with them for a little bit, and then you're like, all right, why don't you go play this game with Lil'Flo? I'm gonna go talk to another patient, right? And so you can still have those interactions keep going. So that's part of the motivation. But I really, I think that having this sort of peer activity will drive better interactions long term. I do think that's a valuable thing to study, that it would be interesting to try to design a system where the clinician is clearly the robot and see how it compares.
So as a follow-up to that idea of having the clinician being within the 3-agent, someone had asked about how efficient is the robot compared to the real medical personnel in the testing?
So for assessment right now, if you're doing, let's still be talking about telepresence assessment. That's done. What people will do is they'll ask patients over telepresence to do a number of activities. They'll store the video, and then they'll go back over the video. So they'll scrub back and forth, looking for features that they know to look for, and giving a rating. That is highly inefficient, and most clinicians I've talked to do not find that to be the most rewarding part of their job. The idea here is that you can do the same sort of thing. We'll grab video, and hopefully there's enough data there that we can do the same we can provide the same metrics to the clinician. And by the measure of clinician time, that is significantly more efficient.
Yeah, that's a good point. So one of the things that was asked was about the digital, your design of the face. Ming Wang asked, is it possible to make the whole face a digital screen and to better express more information?
Yeah, so we actually tried that in one of our earlier prototypes. We had a few different LCD screens that we slapped in there. It can be done. If you want a great example of that being done, Moxie is coming out from Embodied, and they've done that really, really well. For us, the challenge was fitting the LCD screen in there. So the amount of bezel that we have off the kind of screens that we can buy at our scale, they're not ideal. But then even more importantly, the brightness of the screens is so low that you have to make the screen visible. And so you end up with this kind of jarring thing where you have the screens kind of visible and maybe there's something like darker around the screen. It just doesn't create the full integrated experience that we want. I mean, the other challenge that you have with the full screen is that now you have this huge design space to run with. So here there's a limit to how many faces and combinations of eyes and faces we can make. But with a digital screen, you've really made it to where you can do a lot. And you need to have the design team to be able to handle that.
So a follow-up question on the whole uncanny valley and your decision to try to avoid that. William asked, how have you gauged how people react to the different features of the robot?
So I think that the idea is individually, right? So the face versus arms. I don't know that we've been able to break it apart to that level. We did have the study with just the head and face, and it was not in the uncanny valley, I don't think, but it might have been uncanny to have a robot head just mounted on a box with a sheet over it. And so some people talked about that, about how they didn't like not being able to see the rest of the body. So I will say that parts of robots on their own, I don't think fall into the uncanny valley, but they fall into some sort of other uncanniness where it's disturbing, potentially to certain people. But just interacting, having the robot interact with people, it's interacted with, it's hundreds of people at this point, kids during outreach events, people in the hospital, with patients and clinicians, the security staff, like everybody. And the number of people who find it to be creepy or uncanny is very small. And when I ask them why, it's almost never because I feel like it's kind of like a person, but not a person. It's almost always because they say something about Terminator. They say that like this robot's can take over the world, which is ridiculous. But.
So you have a question about the intensity of your hardware and software, because you mentioned that it was intensive hardware and software requirements for this non-autonomous system. The question was, is it a feasible possibility to make this an autonomous type system one day? And is this already a goal, and would it require a complete redesign, or could it be incorporated into a different iteration or the current design form?
So I would say that from a hardware perspective, it's a very easy change. We need a little bit more power on the system, so we need a bigger battery, and we need a better compute system. So right now we're using a NUC. We would probably go to a Jetson Xavier type system is what's out there right now. So something with GPUs on it, or maybe both potentially. It's something that we've talked about doing, and that I keep having to fight myself to not do, because I really want to play with the autonomy of it, but I also want to finish my PhD. From the computational side, it's much harder. I think basic things like keeping track of what the robot's doing, whether somebody's doing the motions that correspond to it, and correcting them, that is very feasible. Conversational autonomy is much harder. And so again, I'll reference Embodied that just released Moxie. They have an example of a conversational AI agent, and it's taken a large team a long time to develop that. That's definitely beyond my abilities, but there's no reason why you couldn't hook into the cameras that are there right now, hook into the voice generation system, the motion generation, the face generation. It's all designed to where, intentionally from the beginning, to where you could hook in and add intelligence, because we've always wanted to. Originally, I had this idea that the robot would autonomously try to express empathy with people. So as they were struggling, that was the first thing I wanted to implement, that the robot would express struggle. If somebody wasn't able to complete the motions, the robot would also be like, wow, this is really hard and not be able to complete the motions. I haven't gotten to that, but I don't really think the jump is that huge.
We've also explored with one of the previous students looking at kind of what it would mean if the robot was autonomous within a hospital environment. So I think we've thought about it. We've just not kind of focused on implementing that right now.
Well, yeah, and that brings up a totally different type of autonomy than even what I was talking about, which is valuable to discuss, which is the navigational autonomy. So we've had a number of challenges when we've been testing it for COVID, or with patients during this COVID time. The two biggest ones have been people being able to hear the robot and networks dropping out. And so when networks drop out, the robot generally finds a way back onto the network and you get it back in a moment. But you still have this kind of like dead time where it's driving. And so being able to navigate around the hospital, and there are a bunch of people who are working on that in GRASP, would be really valuable, because now you could say, go to the place, right? You know where all the network dead spots are. If I'm driving it, don't let me go into a network dead spot. If you're driving it, that's fine. Just get back into a regular spot. And if you do ever die, come back to safety. And so I think there's a lot of autonomy that doesn't even show up in the humanoid that would make the experience of operating the robot significantly better, and should definitely be on the pipeline for things like this.
Michael, while you're talking about COVID, a question came up as to, have you had any feedback from the clinicians as they are working in the with COVID patients?
So most clinicians are concerned about COVID that I've interacted with. So the way that rounding generally works, at least in a teaching hospital, you will have a large group of people going into every patient room. The patient rooms are set up to accommodate that. And so now you've got an attending, potentially a chief, and then a few of the younger residents going in, maybe some med students as well during normal times. That's a lot of people to be going into a room. And so they've been really interested in how can they decrease that. Some other people in GRASP took the approach of putting static cameras and screens into rooms for some types of monitoring, but that doesn't seem super feasible at the scale that a mobile robot could cover, right? Where you want the robot to be in the room for a couple minutes, then be out. There have been significant concerns around cleaning, and so that's been one of the challenges we've had to tackle. And so we've met with multiple infectious disease people. They've examined the robot, they've studied it. There are things we had to modify on the robot. But we go take the robot around, somebody's got to wipe it off with hydrogen peroxide wipes each and every time it comes out of the room. And so that's a challenge. We closed the back of this so nothing can get in there, so that's wipe downable now as well. So yeah, there are definitely challenges to that. And the goal of what they would really like is to have a system that's docked on the floor. It has a fully integrated power system. They can log into whenever they need to and drive it around. But we were at, Dr. Johnson and I, a couple weeks ago, this summit of roboticists discussing infectious diseases and robotics. And, I brought up the point that these robots can't even open doors. Like, nobody's robot can really open doors. And so there are significant challenges to deploying this. Can you actually put it into a restricted floor where there are doors all over the place to protect people? Not really. And so we're at the early stages of testing, driving feasibility, and trying to build more interest in this sort of thing. And I think that interest is coming fast. I think a year and a half ago, when I would discuss telepresence robots with people, a few people would be excited. A lot of people were just kind of like, meh, whatever. We like the way we do things now. And then now everybody's excited.
Yeah. You have one last question from Pratik. You asked about the haptic feedback interface. How apt will it be, especially for blind and or deaf patients? If we were working, what would you have to do there? And then we need to wrap up. Okay. Last question.
That's interesting. I'll be honest, I haven't thought about it in that direction. There are people in the lab who've built on-joint sensors, but never haptic systems. And I think that the way you would think about building these entire interactions would be vastly different for somebody who was especially totally blind. For somebody who's deaf, I think a system like this has a huge argument, because right now, telepresence for somebody who's deaf, it's not good. But if you have a robot that's now moving around, at least they can understand that. And you've got a screen you can put captions on. So the screen can be used for more than just showing the clinician. Yeah.
Well, thank you everyone for coming to Michael's talk. That would be the end. We're at the last hour. Thank you, Michael, for a wonderful talk. And what do I need to do, Peter, to wrap up? Anything specific?
Nothing. I'll just end the meeting now. Thank you so much, Michael. Thank you, Dr. Johnson. This was really, really great.
Okay.
Thanks everybody for coming.
Thank you. Bye.